Hi, we're going to continue our discussion on the formed elements with platelets, which is our cell fragment. The platelets are cell fragments, all right, that come from megakaryocytes. Megakaryocytes are cells that shed off pieces, and these pieces are what we call platelets, and we refer to those platelets as cell fragments. These cell fragments contain clotting factors. These platelet goes into actual circulation. So the megakaryocyte stays mainly into the bone marrow, and some of these, extensions and breakaways cell fragments are the ones that go into circulation. These platelets stay in circulation for about 9 to 12 days. Out of all the cell fragments that are, broken off, 2/3 of them are in blood, and about 1/3 remains in the spleen. So the spleen is a highly vascular organ, and it picks up all those platelets that are about to be disposed of, and it phagocytizes them. We want to remove those cells that are about to be, that are about to die or about to be break open, because if they break open into circulation, they're going to release, clotting factors, and you're going to have blood clots throughout. So you want to phagocytize them when they're about to degenerate themselves. These are a few concepts that you should keep in mind. Platelets are the second most common element of formed elements, and we use the term thrombocytopenia to describe an abnormally low platelet count. All right, there are multiple reasons why there may be a low platelet count, either be that there is low production, or there is abnormal high consumption. Right? So if you are bleeding, it means that you're consuming more platelets because your body is trying to stop that bleed. So this could be one of the reasons why a person may have thrombocytopenia. Thrombocytosis is alluding to the idea that there is an abnormally high count of platelets, and there may be an abnormally high count of platelets if, one, there is a high production of platelets. So if the megakaryocytes are producing a high amount of these elements, and it may be because of infection, inflammation, or cancer, right? So key three functions for platelets. They release chemicals that are used within clotting, all right? They themselves temporarily plug the vessel when damaged, and they contract to reduce the break in the vessel wall. Let's talk a little bit about each one of them. So when picture a vessel that has been ruptured, all right, there is something happens here. Now, the exposure of the tissue will lead to the aggregation of platelets to this section. We're going to picture this as platelets. These will aggregate here, and when they aggregate themselves, this causes an activation and the release of those clotting factors. And those clotting factors will enhance more clotting. And we'll talk about hemostasis in a second. But it is that activation that leads to a patch to prevent the blood from continuing to leak outside. Now, let's talk a little bit about the plug. Platelets attach to themselves, and as they attach to themselves, they can create a plug. Now, this plug is temporary, and this plug can then contract. So, picture this is the vessel right here. Let me just erase this. So there was an injury here. Now the platelets aggregated themselves and now they plug that break on the vessel. They will start contracting themselves, each one of them, they will start contracting to try to seal this off. Okay. How are they made? We name the process of platelet creation to something that is called thrombopoiesis. Remember that poiesis is the root name for creation, and thrombo means clot. Some people may term this as thrombocytopoiesis. So cyto means just cell. They both mean the same. So this is clot cell, clot cell creation. All right, and this creation starts in the bone marrow, and they come from hematopoietic stem cells from the myeloid lineage. Hemocytoblast is the same as hematopoietic stem cell. It's the same as hemocytoblast. Hemocytoblast just means that this is heme, this is blood, all right? Cyto means cell, and blast means early forms. So early forms of blood cells. Early forms of blood cells are then differentiated into the myeloid lineage, right? And from the myeloid lineage, as we saw, there are multiple red blood cells, white blood cells, and now we also have megakaryocytes. These megakaryocytes are huge. They are very large. They then break down into platelets, right? The megakaryocytes themselves live for a long time, but it is the plates that break off that are being phagocytized later on in the spleen for recycling much sooner than what the lifespan of the megakaryocyte itself. The hormones that increase platelet production are thrombopoietin and multi-CSF. Remember from the lineage of the hematopoietic stem cell that can either be a lymphoid lineage or myeloid lineage. Now, from the myeloid lineage, you have multi-CSF, so multi-colony stimulating factor. So this will go here. Multi-CSF. Let me just put that in black. Now, multi-CSF will then help for the creation of the different lineages, and that will be red blood cells, granulocytes, and megakaryocytes. Karyocytes. Okay, so the megakaryocyte, let me just put here, megakaryocyte, this myeloid lineage, once produce all of these colony forming units, knows that it has to focus on the megakaryocyte one because of thrombopoietin. Thrombopoietin stimulates this colony forming unit and it helps for the creation of the megakaryocyte itself. EPO erythropoietin will stimulate the colony forming unit of the erythrocyte and it will help with the creation of red blood cells. We have GM, granular and monocyte stimulating factors that will work here and for monocytes as well. Okay. So in summary, the key takeaways from platelets is that platelets are cell fragments, and as such, they don't have a nucleus. Okay, they do have coagulating factors within the release molecules that help in inflammation. They're the first to encounter and to help with that hemostasis or help reduce bleeding by creating a platelet plug. And remember that when they create a platelet plug, then once they can contract with the help of actin and myosin to reduce the site of injury. They play a role in hemostasis, they clump together, they stick to the basal wall, and they play a huge role into the intrinsic pathway. We'll talk about this in the next slides. Remember that they come from the cell of the megakaryocytes in the red bone marrow. So we talked about platelets playing a role into the cessation of bleeding, hemostasis. Hemostasis is the process by which your body prevents blood loss in the case of an injury. Now there are three key pillars to that hemostasis process: the vascular phase, platelet phase, and the coagulation phase. All right, let's start with the vascular phase. The vascular phase is triggered with vascular spasm. All right, so the smooth muscle from that vessel will contract to reduce the amount of blood flow that is escaping, and in doing so, it will expose base membranes to the bloodstream. All right, so let's say we have a blood vessel that has been cut. This break will cause a contraction of the smooth muscle so that it later looks like this. And this contraction can last for 30 minutes while this is patched up by a platelet, a plug, or something else. But those endothelial cells contract. All right, you should keep that in mind. Now, the endothelial cells release factors here. And these factors are used into the patching process, which is in the other phases, but just note that they are released. And they also release endothelins, which are the ones I help you with, that contraction. The endothelial plasma membrane becomes very sticky, eventually closing this end off. In this picture, it shows some of the same things that we looked at before. Endothelial cells contract, releasing endothelins that stimulate smooth muscle contraction. So when they break, endothelins are released, leading to the vascular spasm. All right. We're also releasing ADP, tissue factor, and prostacyclins. And these ones play a role into the different phases of clotting. But the end goal of this is to decrease the amount of blood loss. So that brings us to the next step, and that is the platelet phase. The platelet phase, remember that in circulation we have platelets. These are inactive. However, as soon as there is a break in the blood vessel, all right, there's a break right here, we're going to expose endothelial cells, basement membranes, and collagen fibers to that blood. So these platelets that were here, inactive, now exposed to those collagen fibers, they become activated. And once activated themselves, they recruit other platelets themselves. They release chemicals, creating a positive feedback loop where the collagen fibers recruit platelets and the platelets themselves recruit other platelets. And it is within this platelet plug that they can contract to reduce the site of injury. This is another way to depict it. So remember that the platelet phase of hemostasis begins with the attachment of platelets to the endothelial surfaces. Once there is a break, those basement membranes, collagen fibers, activate those platelets. And as you activate the platelets themselves will recruit other platelets and stick to them. Okay, that is what creates a platelet plug, and we call this aggregation. some of these factors that are released by the breakage in the tissue that were released during the uh, vascular phase, ADP, and platelet factors are here. That enhances that platelet aggregation. Finally, the coagulation phase. So in the coagulation phase, we are activating different pathways to get to our final goal, which is the creation of something that is called fibrin. Fibrin is a mesh that is capturing multiple cells and creating a much more stable um, plug to prevent blood loss. Although the platelet, plug may help a little bit, it's not as stable. It is within fibrin that it will enhance and will make that clot, that mesh stronger. So in conclusion, we have multiple pathways within this coagulation phase. We have a total of 3 pathways. All right. You should know that they are the intrinsic pathway, the extrinsic pathway, and then the common pathway. And they all end with the same result, which is the creation of fibrin. We're gonna discuss in detail how is it that we get there. The process of the coagulation phase starts about 30 seconds from the site of injury. The blood changes from a smooth liquid to a gel because it's coagulating during this process. This process or these pathways are basically a series of cascade reactions that are changing over time. We have proenzymes or enzymes that are inactive and they start to become activated. And then when they are activated, they activate other enzymes. And that is what we call a enzymatic cascade. All right. So during this coagulation phase, the goal is to make the blood really sticky, and then we're trying to convert blood into gel via a series of chemical reactions to create fibrin. These cascade reactions is involving clotting factors such as calcium, enzymes, proenzymes through the 3 pathways, intrinsic, extrinsic, and common, with the end goal of converting fibrinogen, which is an abundant protein in blood, into fibrin. This is a quick summary of some of the factors that are involved into hemostasis, more so into the coagulation phase. Now we already know some of them, so let's take a look at some of them. This one, factor 1, is fibrinogen. Fibrinogen is circulating in blood, but is inactive. It is once, once it is converted by a certain enzyme that is converted into fibrin. All right, and fibrin is the end goal of all these three coagulation pathways in order to create a mesh. This mesh is what helps create a stable blood clot. Okay, now we have prothrombin. Prothrombin we haven't talked about, but this is going to be a part of that coagulation cascade. We've already talked a little bit about tissue factor. Tissue factor, remember, that is released when you break the vessel. When you break the vessel, not only you expose the blood to collagen membranes and basement membranes, but you also release tissue factor. This tissue factor is also known for factor 3. Okay? You know about calcium ions. Calcium ions, they used to be thought to be a factor, but we don't term this as a factor 4 anymore. We just say that we're using calcium ions. All right. The Out of the other ones, we haven't talked about the other ones. Okay. Now, another key takeaway from the naming of these factors is that they were not numbered or named based on where they come in the cascade. They were numbered when they first appeared. So you may find that in the cascade, you may use a tissue factor 12 to give rise to tissue factor 9. So it is not based on when they appear in the cascade. They are just numbered based on when they were first found. Okay, so hemostasis, remember that is the cessation of blood. And we want to try to accomplish this to avoid bleeding. So whenever there is bleeding because of an injury, we start a hemostasis process, and that has three main phases: vascular, platelet phase, and now we are into the coagulation phase. The coagulation phase is divided into three pathways: extrinsic, intrinsic, and common. And the main goal outside of all of these is to convert a fibrinogen to fibrin, which is a mesh that makes that clotting process more stable. It coagulates that blood so that there is no more blood loss. We're going to start with the extrinsic pathway. The extrinsic pathway begins outside of blood. So as soon as you damage the vessel, you release tissue factor 3. And this tissue factor 3, in combination with calcium ions and factor 7, they create an activating complex that activates tissue that activates factor 10. So we have the blood vessel, it breaks, and then you release tissue factor 3. Okay. Now calcium ions are free flowing in blood. So as soon as that happens, this in combination with this now factor 7 is also free flowing in blood. So they connect together, they create an enzymatic complex. And this enzymatic complex goes on to activate factor 10. Factor 10 is inactive in blood. But as soon as it is activated by these complex of molecules, you can think of factor 3 plus 7 gives you 10. So you have now activated factor 10. And this is, we're going to leave it here. This is the end of the extrinsic pathway, but it is where the intrinsic pathway will end as well. Okay. So the intrinsic pathway starts with the activation of factor 12. As soon as there is a break in that vessel wall, those basement membranes as well as the collagen will activate that tissue factor 12, which was circulating in flood inactive, but as soon as it became, it came in contact with those collagen fibers, it became activated. Now this factor 12 that is activated will go on to, in addition to other enzymes, to convert factor 11 into factor 9. And it is factor 9 in conjunction with platelet factor 3. So we're going to put in here 9 plus PF3 plus 8 that will go on to create a complex that also activates inactive 10 into factor 10 that is active. Both intrinsic and extrinsic pathways, their main role into the coagulation cascade is to create factor 10. Okay. You don't need to know the specific of which role did what, As long as you know the bolded terms, I am happy with that. But you should know that we have the extrinsic pathway and the intrinsic pathway, both giving rise to the activated factor 10. Okay, so they are both doing the same. The intrinsic pathway is doing this a little bit different than the extrinsic pathway. The intrinsic pathway, again, does it by activating free-flowing factor 12. Okay, it became factor 12 because of collagen. Okay, and the basement membranes, it activated it. Now, factor 12, in conjunction with ions, will go on to convert factor 11, which is inactive, into 9. And this will play a role right here. Now, factor 9 that is active, in combination with factor 8 plus platelet factor 3 plus calcium ions, it will go on to create an enzyme complex that activates inactive 10 factor into active 10. X, remember that it starts for 10. Okay, so remember the terms, the intrinsic pathway. It starts with the activation of a factor through collagen fibers. These are proenzymes. We're referring to factors such as number 12 that are in blood. Now, as soon as those platelets start aggregating, they start also releasing this factor, platelet factor 3, and then in combination with some of these proenzymes and cascade reactions, you will end up with the result of an activated form of factor 10. That brings us to the common pathway. So, in summary, hemostasis is happening because we're trying to stop blood loss. So your body has three mechanisms by which it does that: through the vascular phase, the platelet phase, and the coagulation phase. We're going through the coagulation phase. Now, the coagulation phase can go through three specific pathways: the intrinsic and the extrinsic pathway. The nuance to this section right here is that the common pathway doesn't start until it gets here. So the intrinsic pathway will both end where the common pathway starts, and this is where we create fibrin. So the end goal of this coagulation, let's put it in blue, phase is to create fibrin, all right? And it does that through the intrinsic and extrinsic pathway, getting to the common pathway to convert fibrin. We already discussed a little bit of how it is that the extrinsic pathway does that. When the vessel is injured, you release tissue factor 3, and this tissue, the tissue factor or factor 3, in addition to calcium, then goes on to activate forms or proenzymes of factor 10 into an active form of factor 10, which is ends right here. So the common pathway started with factor A. Okay. Now, as far as the intrinsic pathway, we know that the intrinsic pathway starts with the exposure of those collagen fibers, activating a proenzyme, which is factor 12. And once a proenzyme is activated, this complex, it becomes a complex that then goes on to convert factor 11 into factor 9. And that factor 9, in addition to factor 8, plus platelet factor 3 plus calcium ions, they're going to create a complex that converts inactive factor 10 into active. So the intrinsic pathway also ends onto an activated form of factor 10. So that brings us to the common pathway. So the common pathway, it is where the intrinsic and the extrinsic pathways converge. They start with the active form of factor 10 to form the enzyme that is called prothrombinase. Prothrombinase then goes on to convert prothrombin into thrombin. So we have prothrombinase, and we're gonna put it into different roles, and we have free flowing prothrombin in blood. But this prothrombinase comes in and changes it. And now prothrombin becomes, let's put it in blue, thrombin. Now thrombin is another enzyme, goes on to convert fibrinogen into fibrin. Okay, and this is done by the enzyme thrombin. This fibrin creates a mesh that traps red blood cells, platelets, and it stops bleeding. So we have the different pathways. Remember that coagulation phase or blood clotting involves a complex sequence of steps leading to the conversion of circulating fibrinogen into fibrin. And it is this fibrin that helps the blood cells. It helps like a spider web to trap all the red blood cells or the platelets and create a blood clot to prevent a blood loss. Now we go through the different pathways. We have the extrinsic, we have the common, and we have the intrinsic. So let's just start with the extrinsic pathway. Remember that when there is a damaged vessel wall, that vessel wall will release tissue factor 3, and that tissue factor 3 in combination to calcium and factor 7 create a complex that goes on to activate inactive factor 10 into activated factor 10. Now the intrinsic pathway is a little bit more delayed, but it starts with the activation of factor 12, okay, from that collagen. And that factor 12 undergoes a series of revisions and it ends up forming a complex in addition to platelet factor 3, all right, that creates an activated form of factor 10, okay? And factor 10 then goes on to transform into prothrombinase. Prothrombinase is the actual enzyme that carries on the function of converting prothrombin into thrombin, and then thrombin is the active enzyme that goes on to carry the conversion of the fibrinogen into fibrin. In hemostasis, we have also something that is called feedback control. So thrombin stimulates clotting by positive feedback. Thrombin is releasing tissue factor, which remember is playing a role into which pathway? The extrinsic pathway, all right? And now it also releases platelet factor 3, which plays a role into the intrinsic pathway. So this thrombin molecule enhances the production of these molecules that by their nature create a cycle, a positive feedback loop, accelerating clotting. Now there comes the other side. We want to control the amount of clotting that occurs, otherwise you're going to end up clotting your entire body. So the body, at the same time that it starts to coagulate blood, it starts the opposite process, and that is the removal of that clot to allow healing. Now, the key takeaway here is that that happens a lot slower. All right, let's take a look at how that works. So, plasma contains antithrombin, which inhibits multiple factors, including thrombin. So, as soon as we start clotting, there will be some forms of inactivated thrombin. Basophils and mast cells will release heparin, and this increases the activation of this thrombin right here. And the goal is to decrease coagulation. All right. Endothelial cells release other molecules, all right, that inactivate other clotting factors. So further decreasing that, trying to decrease that positive feedback communication between thrombin, tissue factors, and platelet factor 3. Prostacyclin inhibits platelet aggregation. And then fibrinolysis is the slow process of dissolving the clot. Thrombin and tissue plasminogen activate or activate plasminogen. Plasminogen produces plasmin, and plasmin digests the fibrin. So remember that thrombin plays a role into the formation of fibrin. It is also doing the opposite. Now, the creation of the fibrin happens faster than the creation of this plasminogen. Okay, so that there is a balance. Keep in mind that in this blood clotting cascade, there are multiple ions, and some of these factors are dependent to vitamin K. All right, so at a high diet in calcium may increase your coagulability state. A diet rich in vitamin K will enhance the odds that you may develop a blood clot. Now, we use vitamin K as a form of therapy and as a form of inhibition when we want to control and modulate these blood clotting factors. All right, because vitamin K is needed to produce clotting factors. Warfarin, it antagonizes vitamin K. All right, so if we antagonize vitamin K, we cannot produce these blood clotting factors, so that means that the person will be less likely to make a blood clot, so we thin out their blood, so to speak. All right, this is a just a summary going back to some of these factors. Now we know with each one of them, where they play a role. So let's just go through a quick summary of them. So fibrinogen is free flowing in blood, and the end goal of the coagulation phase is to convert fibrinogen into fibrin. All right, fibrinogen is made by the liver. So if a person that has, if a person has liver failure or long-term liver disease, will have low amounts of fibrinogen. So you should consider that patients with liver failure will be at a high risk for bleeding because they don't have enough fibrinogen. All right. We have prothrombin. We talk about this also is a precursor molecule where we are trying to activate prothrombin into thrombin. Okay, this prothrombin is made out in the liver and requires vitamin K. Now that brings us to factor 3. Tissue factor 3 is released by damaged tissue. All right, we're gonna just keep it on damaged tissue for now, and this is the beginning of the extrinsic pathway. All right, calcium ions, although it is mentioned as calcium 4 as factor 4, we don't really term it as factor 4 anymore. We just go ahead and use calcium ions. all right, and this is used on both pathways, intrinsic and extrinsic, as well as the common pathway. Factor 5, we didn't talk about it, just know that it plays a role on both extrinsic and intrinsic. Actually, you don't have to know about factor 5 just yet. Um, we didn't cover that, but just know that it's a factor that plays a role into the coagulation process. We have now factor, let me see, did we go over factor 7? So factor 7 in combination with factor 3 gives us the complex that converts factor inactive for factor 10 to activated factor 10, and this is part of the extrinsic pathway. Okay, it's made in the liver. We have factor 8, and factor 8 is part of the intrinsic pathway. Remember that it combines with factor 9, calcium, and a platelet factor 3 in order to create this complex that converts inactive factor 10 into active factor 10. We have factor 9 that is also part of the intrinsic pathway. All right, this requires vitamin K, and this is part of that complex that combines with factor 8, a platelet factor 3, and calcium in order to create this huge complex to convert factor, inactive factor 10 into activated factor 10. This is factor 10, all right, which is free flowing, and it is activated by multiple complexes, either be from the intrinsic or the extrinsic pathway. Factor 11, it is we just talked about it briefly, but this is converted to factor 9 by factor 12. All right. And so if you were to be asked which factors are affected by vitamin K, you will say factor 2. All right. Which other one? It will be factor 7, factor 9, and then factor 10. So these 4 are part of the vitamin K process. So if you inhibit vitamin K, the liver won't be able to make the precursors. You won't be able to make prothrombin. You won't be able to make factor 10. All right. And so this is how medications like warfarin can prevent blood clots.